Welcome to Kaiser Neuromap Institute. We are presenting brain maps of the same individual recorded 3 years apart, once at age 16 and once at age 19. The latter recording was during a mental health and drug-related crisis. Let's call him Lorenz, not his name, and review his neurolimbic assessment. Scientists and clinicians have been analyzing brainwaves for 100 years. 1924 was the first human recording, 1929 the first publication. We have learned a lot about brainwaves over the century, with more than 200,000 peer-reviewed publications in PubMed and nearly 2 million papers on Google Scholar. Let's begin with a brief history of Lorenz. He is a 19-year-old college dropout. His mother felt he was lost and brought him to us for help. He was smoking marijuana, acting out, being aggressive, and getting into trouble with his friends. When asked about his career goals, he says he might like to be a graphical artist, but is not sure. Expertise in graphical arts begins with practice, which is the reason why you're looking at a box containing Greek letters. He was instructed to go ahead and every day or few days create an image out of some Greek characters. Make a single-page story, for instance. Show them at a table or having a picnic. Write down the date of each creation, and over time, he'll see how much he improves in graphic arts. This is a simple way to get feedback by practicing daily and later reviewing the results. Feedback is how we improve. Feedback allows us to learn and be successful. At age 16, he was very shy. I hardly remember him. When he came in at age 19, he was like a wild animal. I was very nervous to record him because he acted so raw. We compare activity and connectivity of brainwaves to a very healthy group. This comparison reveals how deviant any measure is statistically from the norm. We start with a surface montage of 19 electrode sites. Each trace is labeled by 1 or 2 letters followed by a number. Odd numbers indicate the electrode is positioned on the left hemisphere, left side of the head, and even numbers reflect electrode's position over the right hemisphere, right side. The letter Z stands for 0, the midline. FP stands for frontal pole, then F for frontal areas, C for central, T for temporal, P for parietal, and O for occipital. 19 brainwave traces are recorded from the scalp. We keep in mind that EEG sensors are similar to microphones in a room where everyone's sitting around a table. When anyone talks, many of the microphones pick up this sound, and using this knowledge, we can triangulate activity of each source or person in this example. When analyzing EEG signals, they're composites of signals from multiple sources for the most part. A couple channels like PZ and FZ are strongly linked to a single source in the brain, the anterior and posterior cingulates. But for the vast majority of sensors, many neocortical sources are contributing to a single site's recording. For instance, activity recorded at electrode site P4 comes largely from area 39, some area 40, and a little from area 7. Many sources contribute to a surface EEG recording. We can triangulate down to these sources, which allows us to see much more interesting signals, more accurate and less noisy. Notice the spindle activity. That's the alpha activity, waxing and waning. You can observe alpha activity in the occipital lobe. When eyes are closed, we want to have a lot of alpha. Alpha activity indicates this part of the brain is idling, not working much, as nothing's being asked of it. During our eyes closed resting recording, we instruct the individual to close their eyes and let their mind wander, let thoughts come and go. We are looking at a short snippet of information, 10 seconds in length, simply to get a feel of the EEG signal before analyzing further. We also record during eyes open and instruct the individual to look at one of the picture on the wall. Each condition is recorded for 3 minutes at a time, 3 times each. This is called dominant or peak frequency when eyes are closed and resting. We focus on the right column, 7 to 14 Hertz, as the overall column can be contaminated with artifact like eye blinks. Sometimes this column may have harmonics in it. We care more about the 7 to 14 Hertz column on the right. Each row are 19 regions of the brain, some of the left side of the head, some on the right. We also pull out an additional area on the left side called Broca's area. The right dorsolateral has 5 Brodmann areas, and the left has 3, with 2 more areas making up Broca's area for 5 in total, just like the right hemisphere has. Reviewing the values in the table, We'd like this all to be consistent, and we'd like it to be around 10 Hz, the adult range. In other videos, I explain why 10 Hz is the optimal speed, but not for everyone. We don't want to be too fast. If peaks are 11 to 12 Hz, that's the adolescent speed. Work harder than most people. If peaks are slower than 9 Hz, such as 7 or 8 Hz peak frequency, sensory processing is slower compared to most people, and this may cause occasional communication friction when interacting with someone processing much faster, especially in a noisy environment. Okay, so what we do is Fourier analysis. We take a signal and convert it to a spectral plot. And once it's in a spectral plot, we've learned certain things. For instance, a maturational development occurs for these plots. Plots start off looking like this slope called pink noise. This indicates a lack of sensory processing, hardly processing the sensory world, and as we progress down the row, we see more and more sensory processing, more in balance with the sensory world and more efficient. In the low end of the plot, excessive amplitude or height is typically not a good thing to have during eyes closed rest. On the far end of the plot, we may be concerned about excessive amplitude or bumps as they appear. Those are called harmonics. We'll go over more details about harmonics in another video. We splay out three-dimensional space in a two-dimensional depiction. Top row shows regions where we make decisions located in the front of the head, dorsolaterals. Bottom row shows visual processing area. There are parietal regions and somatosensory. We are showing three-dimensional information in 2D, so spatial location is only general, not exact, in spectral plots. They would share the same space, but it would be too crowded there, so we put the somatosensory in this location. You can see what we want is alpha peaks. That's what we want. We don't want all this energy, all this height over the 7 in between, like 5 to 7 if there's a 5 there. We don't want that 4 to 7. Okay, so what you see in the 3 years that happened, slight improvements. We see a slight little alpha, but there was no intervention. Now, usually I have brain maps of people like a pre and a post. They've gone through neurofeedback treatment or residential treatment, or there has been an accident and possible brain injury. It's unusual to have a recording pre and post with no intervention between recordings. And the reason why I bring this case up is to show how reliable two specific parameters of EEG are. Most EEG is really good at moment-to-moment changes of what's going on in brain activity. We don't want those what's called state parameters. We want trait parameters. We don't want the moment-to-moment changes. We want the habits. We want strong circuits that are coordinating together because that's what we want to do. Because those are the ones of the habits that reflect the behaviors that reflect clinical symptoms, such as depression and anxiety or whatever the reason the person's seeking neurotherapy. The color pink indicates excess and blue deficiency for each frequency measured. Notice how Lorenz has a deficit in the beta range with a little bit of excess in the alpha range. Notice how reliable it is. Pretty reliable, a little bit changed, but it's pretty reliable. Entropy reflects activity, and the another measure analyzes connectivity, called unity, which is even more reliable as a trait measure. Think of the brain as a two-story house. The first floor is our primitive instinctual reptilian brain, and this floor gets built over the first 5 or 6 years. That is the subcortex, the limbic system, which includes the hippocampus, amygdalas, and hypothalamus. Hypothalami, as there are 2 of them, one in the left hemisphere and one in the right, as with most brain areas. Those things get developed, mature early. They get wired early in development, and so they control the young child for a number of years. When this section of the brain, the subcortex, is in charge, it has immediate goals only, like a reptile, stimulus control goals. If there's something to eat, go after it. Another aspect of subcortical thought is that everything's relational. There is relational thinking, and relational thing means everything's about that person, about me. Thinking, I'm the center cosmos. Anything happens, the environment, it's about me. And that is how we all start off as children. We observe language development in toddlers, which follow this path. They start out relational, and after a while they start including and connecting and integrating with the neocortex on the second floor. This floor, the neocortex, has 10 times more cells, 10 times more room. To stay with the house analogy, to represent what's going on in the world. We go from relational thinking to object thinking, where objects are perceived as independent of us. Last night I was walking inside and a dog cued on me when I was heading to the elevator. He was in that relational thinking mode. He kept looking at me, thinking I'm acting because of him. What I'm doing relates to him, in his thinking. And it kept looking at me, thinking I'm acting or moving this way because of him. But of course this is not true. I'm independent. I'm going up to my apartment and taking the elevator up, but he couldn't keep his eyes off me. We want to minimize relational thinking habits, which is what our neurofeedback does, called DNT or default network training, for another video. It's unhealthy to be constantly relational. There's a spectrum of relational thinking to this object thinking, or independent thinking, and we want to find a balance point where our goal-directed thought controls our actions and habits, and not letting the environment control us. With our Neuromaps, we evaluate 55 brain areas and 19 brain regions, allowing us to recognize when a brain region is letting the bottom floor control the individual instead of the top floor, the neocortex. We observe this in brainwave connectivity. Our measure reveals functional transparency of the corticolimbic area. In essence, how similar is the activity in all directions and areas. When our measure is orange, it's hypersimilar. And that is an indication that the neocortex is letting the subcortex dominante and pass through largely unchanged and not repurposing instincts into social behaviors. This happens when there's not enough gray matter or white matter in the area. An opaqueness occurs in our measure as the neocortex matures and contributes significantly to our mentation. A neuromap consists of maps of Brodmann regions and 3 sets of maps of Brodmann areas: posterior, central, or medial, and anterior areas. The Brodmann Atlas was created in 2008, summarizing the scientific literature and what issues are associated with each area or region. Okay, we see with this kid at age 16 showing great transparency in the cingulates and the occipitals and a little bit in the orbitals and the temporal lobe. 3 years later, because there's been no neurotherapy, he's very similar. You see the blue and the dorsolaterals. Orange cingulates is associated with depression, anxiety, and even psychotic risk. It often shows in someone at risk for a psychotic break in episode. His 5-year-old mind is in charge. He still thinks he's got the only perspective that matters. You think of like orange means 2. You're too certain of your perspective, and that means you're going to be depressed and anxious because the world has all this independence around it. We all belong in a tribe of 150 people, a group of 150 people. The world around us has a multiplicity of perspectives. We're not the only perspective. In fact, we won't get rewarded much if we're the only perspective because we don't know how to reward ourselves as much as we think we do. The only perspective because we don't know how to reward ourselves as much as we think we do. And so when you let the world in more, you will be more rewarded. The problem with people here, and it's like why it's also a sign of depression, is often there'll be opportunity will knock at their door and they won't answer because it won't toward. They'll say no to it because they don't fully agree in how to do it. Someone says, let's go out and go to this new place, and like, no, I don't want to do that. Someone with an orange cingulates may say, that won't be fun. But someone who didn't have immature cingulates might go there and have a great time. Orange cingulates lead to depression, anxiety, and can even be a marker of psychotic risk. A lot of the murderer rapists show this same marker this kid has. Now, to sort of cut to the chase, this kid would actually be arrested the very next day. So his parent who brought him in, crisis was on him. He was agitated, like having a wild animal in my office. Well, he had this marker. I used to call it my rapist marker, these yellow or orange cingulates, because at first, only rapists had them. I had some murderers who don't have them from the databases we collected. But then eventually a psychotic showed up. Someone who wasn't a rapist, just a psychotic, and he had the marker, and this confirms our suspicion that it's psychotic risk. And that's when an fMRI paper came out about the same time, saying much the same. Now looking at posterior brain areas, and he had an orange PCC, now it changed from the left to the right side. So the right side first over here is on the left side, addiction marker and PTSD marker. By 2007, Ruth Lanius had shown rather definitively posterior cingulate reduction in connectivity with PTSD, post-traumatic stress disorder, We like to call that area the maternal hub, the PCC, posterior cingulate cortices, a network for nurture and self-nurture. Let's look at the central brain area. Now, area 6s, they did change from left to right. Left hemisphere typically deals with familiar situations, right more novel. Area 5 and 6s we found to be what's called personal boundaries and social boundaries. People who have immature yellow-orange Brodmann area 5s and 6s can be a violent and aggressive PT. He also has his ACCs yellow, which is very unusual to see in adults. That ACCs, the anterior cingulate cortex, is where you monitor consequences of your actions. And it usually matures pretty quickly because most people, to fit into society, have to behave in trustable ways. Yellow ACCs often reveal that the individual is not worried about consequences. They don't mind lying to people, even though we can tell often when they lie and they'll ruin the relationship because of lies. Well, he had that. He had some other things too. Here's someone who killed a cop and hanged and hung himself with those ACCs. Another one lit a person on fire. The good news in that DNT training, neurofeedback we developed over the last 20 years, can move orange and yellow areas to the green, to health and balance. Empirically, we've learned what to do to improve every area in our maps and reduce the reptile within thinking and overreaction to the environment. All right, this has been a brief review of our reliable neuromaps at the Kaiser Neuromap Institute. Thank you. The video discusses the reliability of electroencephalography parameters in assessing brain activity, particularly in relation to trait rather than state changes. We highlight the importance of identifying reliable measures for assessing habit formation and its implications on clinical symptoms such as depression and anxiety.